Astronomy is the oldest of the natural sciences, dating back to antiquity, with its origins in the religious, mythological, and astrological practices of prehistory. Vestiges of these are still found in astrology, a discipline long interwoven with public and governmental astronomy, and not completely disentangled from it until a few centuries ago in the Western world. See astrology and astronomy. In some cultures, astronomical data was used for astrological prognostication. Ancient astronomers were able to differentiate between stars and planets, as stars remain relatively fixed over the centuries, while planets will move an appreciable amount during a comparatively short time. Early history. Early cultures identified celestial objects with gods and spirits. They related these objects and their movements to phenomena such as rain, drought, seasons, and tides. It is generally believed that the first professional astronomers were priests, and that their understanding of the heavens was seen as divine, hence astronomy's ancient connection to what is now called astrology. Ancient structures with possibly astronomical alignments, such as Stonehenge, probably fulfilled both astronomical and religious functions. Calendars of the world have usually been set by the sun and moon, measuring the day, month, and year, and were of importance to agricultural societies, in which the harvest depended on planting at the correct time of year. The most common modern calendar is based on the Roman calendar, which divided the year into 12 months, of alternating 30 and 31 days apiece. In 46 BC, Julius Caesar instigated calendar reform, and adopted a calendar based upon the 3651 four-day year length originally proposed by 4th century BC Greek astronomer Callippus. Prehistoric Central Europe. In the last couple of decades, our understanding of the prehistoric Europeans has been radically changed with the discoveries of ancient astronomical artifacts in Central Europe. Bronze Age Central Europeans had a sophisticated grasp of mathematics and astronomy. According to Berlin archaeologist Klaus Goldmann, European civilization goes further back than most of us ever believed. Kozak Circle, Germany, 4900 BC. Among these recent discoveries is the world's oldest observatory. Located in Germany, it is known as the Kozak Circle and discovered in 1991. The enclosure is one of hundreds of similar wooden circular henges built throughout Austria, Germany, and the Czech Republic during a 200-year period, around 4900 BC. While the sites vary in size, the one at Kozak is around 220 feet in diameter. They all have the same features. A narrow ditch surrounds a circular wooden wall, with a few large gates equally spaced around the outer edge. While scholars have known about the enclosures for nearly a century, they were stumped as to their exact function within the stroke-ornamented pottery culture, known by its German acronym, STK, that dominated Central Europe at the time. The Kozak Henge is currently the oldest official solar observatory in the world. On the winter solstice, the sun can be seen to rise and set through the southern gates from the center. It has been observed that the entrances get progressively smaller the closer to the center one gets, which would have concentrated the sun's rays into a narrow path. Being on the same latitude as Stonehenge means that astronomers would have also benefited from viewing the extremes of the sun and moon at right angles to each other. It is also sitting on one of two unique latitudes in the world at which the full moon passes directly overhead on its maximum zeniths. The Nebra disk, Germany, 1600 BC. The Nebra disk dates from 1600 BCE. Found in 1999, not far from the Kozak Circle, it is one of the most important archaeological finds of the past century. It displays the world's oldest known concrete depiction of astronomical phenomena, and was used as an advanced astronomical clock. According to astronomer Wolfhard Schlosser of the Ruhr University Bochum, the Bronze Age Europeans already knew what the Babylonians would describe 1,000 years later. Also in Germany is the Magdalene and Bergmoon calendar discovered in 2011, under the royal tomb at Magdalene in Berg, in Germany's Black Forest. It is the largest Hallstatt tumulus grave in Central Europe, measuring over 320 ft, 100 m, across and, originally, 26 ft, 8 m, high. Its central grave was robbed in antiquity. More recent excavations have recovered the locations of numerous secondary burials placed around the edges of the mound, and of various timber structures, including rows of wooden posts. There is nothing random about the secondary graves, which might be those of relatives or retainers, buried as they died during the years that followed their leader's funeral. The order of the burials around the central royal tomb fits exactly the pattern of the constellations visible in the northern hemisphere at midsummer in 618 BC, while the timber alignments mark the position not of the sunrise and sunset, but of the moon, and notably the lunar standstill. It is the earliest and most complete example of a Celtic calendar focused on the moon, and that following Caesar's conquest of Gaul, Gallic culture was destroyed, and these types of calendar were completely forgotten in Europe, to be replaced by the Roman sun-based calendar. Mesopotamia. Babylonian tablet recording Halley's comet in 164 BC. The origins of Western astronomy can be found in Mesopotamia, the land between the rivers Tigris and Euphrates, where the ancient kingdoms of Sumer, Assyria, and Babylonia were located. A form of writing known as cuneiform emerged among the Sumerians around 3500–3000 BC. Our knowledge of Sumerian astronomy is indirect, via the earliest Babylonian star catalogues dating from about 1200 BC. The fact that many star names appear in Sumerian suggests a continuity reaching into the early Bronze Age. Astrotheology, which gave planetary gods an important role in Mesopotamian mythology and religion, began with the Sumerians. They also used a sexagesimal, base 60, place value number system, which simplified the task of recording very large and very small numbers. The modern practice of dividing a circle into 360 degrees, of 60 minutes each, began with the Sumerians. For more information, see the articles on Babylonian numerals and mathematics. Classical sources frequently use the term Chaldeans for the astronomers of Mesopotamia, who were, in reality, priest-scribes specializing in astrology and other forms of divination. The first evidence of recognition that astronomical phenomena are periodic, and of the application of mathematics to their prediction is Babylonian. Tablets dating back to the Old Babylonian period document the application of mathematics to the variation in the length of daylight over a solar year. Centuries of Babylonian observations of celestial phenomena are recorded in the series of cuneiform tablets known as the Enma-Anu-Enlil. The oldest significant astronomical text that we possess is Tablet 63, of the Enma-Anu-Enlil, the Venus tablet of Amisaduqa, which lists the first and last visible risings of Venus over a period of about 21 years, and is the earliest evidence that the phenomena of a planet were recognized as periodic. The Amu-Elephant contains catalogues of stars and constellations as well as schemes for predicting heliacal risings and the settings of the planets, lengths of daylight measured by a water clock, gnomon, shadows, and intercalations. The Babylonian Guam text arranges stars in strings that lie along declination circles and thus measure right ascensions or time intervals, and also employs the stars of the zenith, which are also separated by given right ascensional differences. A significant increase in the quality and frequency of Babylonian observations appeared during the reign of Nabonassar, 747–733 BC. The systematic records of ominous phenomena in Babylonian astronomical diaries that began at this time allowed for the discovery of a repeating 18-year cycle of lunar eclipses, for example. The Greek astronomer Ptolemy later used Nabonassar's reign to fix the beginning of an era, since he felt that the earliest usable observations began at this time. The last stages in the development of Babylonian astronomy took place during the time of the Seleucid Empire, 323–60 BC. In the 3rd century BC, astronomers began to use goal-year texts to predict the motions of the planets. These texts compiled records of past observations to find repeating occurrences of ominous phenomena for each planet. About the same time, or shortly afterwards, astronomers created mathematical models that allowed them to predict these phenomena directly without consulting past records. A notable Babylonian astronomer from this time was Seleucus of Seleucia, who was a supporter of the heliocentric model. Babylonian astronomy was the basis for much of what was done in Greek and Hellenistic astronomy, in classical Indian astronomy, in Sasanian Iran, in Byzantium, in Syria, in Islamic astronomy, in Central Asia, and in Western Europe. Egypt. Chart from Senmut's tomb, 18th dynasty. The precise orientation of the Egyptian pyramids affords a lasting demonstration of the high degree of technical skill in watching the heavens attained in the 3rd millennium BC. It has been shown the pyramids were aligned towards the pole star, which, because of the precession of the equinoxes, was at that time Theban, a faint star, in the constellation of Draco. Evaluation of the site of the Temple of Amun-Ra Karnak, taking into account the change over time of the obliquity of the ecliptic, has shown that the Great Temple was aligned on the rising of the midwinter sun. The length of the corridor down which sunlight would travel would have limited illumination at other times of the year. Astronomy played a considerable part in religious matters, for fixing the dates of festivals and determining the hours of the night. The titles of several temple books are preserved recording the movements and phases of the sun, moon, and stars. The rising of Sirius, Egyptian, Sopdet, Greek, Sothis, at the beginning of the inundation was a particularly important point to fix in their yearly calendar. Writing in the Roman era, Clement of Alexandria gives some idea of the importance of astronomical observations to the sacred rites. And after the singer advances the astrologer, with a horologium in his hand, and a palm, the symbols of astrology. He must know by heart the Hermetic astrological books, which are 4 in number. Of these, 1 is about the arrangement of the fixed stars that are visible, 1 on the positions of the sun and moon, and 5 planets, 1 on the conjunctions and phases of the sun and moon, and 1 concerns their risings. The Astrologers Instruments, horologium, and palm, are a plumb line and sighting instrument clarification needed. They have been identified with 2 inscribed objects in the Berlin Museum, a short handle from which a plumb line was hung, and a palm branch, with a sight slit in the broader end. The latter was held close to the eye, the former in the other hand, perhaps at arm's length. The Hermetic books which Clement refers to are the Egyptian theological texts, which probably have nothing to do with Hellenistic Hermitism. From the tables of stars on the ceiling of the tombs of Ramesses VI and Ramesses IX it seems that for fixing the hours of the night a man seated on the ground faced the astrologer in such a position that the line of observation of the pole star passed over the middle of his head. On the different days of the year each hour was determined by a fixed star culminating, or nearly culminating in it, and the position of these stars at the time is given in the tables, as in the center, on the left eye, on the right shoulder, etc. According to the texts, in founding or rebuilding temples the north axis was determined by the same apparatus, and we may conclude that it was the usual one for astronomical observations. In careful hands it might give results of a high degree of accuracy. Greece and Hellenistic world. The Anti-Kythera Mechanism was an analog computer from 150–100 BC designed to calculate the positions of astronomical objects. The ancient Greeks developed astronomy, which they treated as a branch of mathematics, to a highly sophisticated level. The first geometrical, 3-dimensional models to explain the apparent motion of the planets were developed in the 4th century BC by Eudoxus of Cnidus and Callippus of Cyzicus. Their models were based on nested homocentric spheres centered upon the Earth. Their younger contemporary Heraclitus Ponticus proposed that the Earth rotates around its axis. A different approach to celestial phenomena was taken by natural philosophers such as Plato and Aristotle. They were less concerned with developing mathematical predictive models than with developing an explanation of the reasons for the motions of the cosmos. In his Timaeus, Plato described the universe as a spherical body divided into circles carrying the planets, and governed according to harmonic intervals by a world soul. Aristotle, drawing on the mathematical model of Eudoxus, proposed that the universe was made of a complex system of concentric spheres whose circular motions combine to carry the planets around the Earth. This basic cosmological model prevailed in various forms until the 16th century AD. Greek geometrical astronomy developed away from the model of concentric spheres to employ more complex models, in which an eccentric circle would carry around a smaller circle, called an epicycle, which in turn carried around a planet. The first such model is attributed to Apollonius of Perga, and further developments in it were carried out in the 2nd century BC by Hipparchus of Nicaea. Hipparchus made a number of other contributions, including the first measurement of precession, and the compilation of the first star catalogue, in which he proposed our modern system of apparent magnitudes. The study of astronomy by the ancient Greeks was not limited to Greece itself, but was further developed in the 3rd and 2nd centuries BC, in the Hellenistic states, and in particular in Alexandria. However, the work was still done by ethnic Greeks. In the 3rd century BC, Aristarchus of Samos was the first to suggest a heliocentric system, although only fragmentary descriptions of his idea survive. Eratosthenes, using the angles of shadows created at widely separated regions, estimated the circumference of the Earth with great accuracy. The Anti-Kythera Mechanism, an ancient Greek astronomical observational device for calculating the movements of the Sun and the Moon, possibly the planets, dates from about 150 to 100 BC, and was the first ancestor of an astronomical computer. It was discovered in an ancient shipwreck off the Greek island of Anti-Kythera, between Kythera and Crete. The device became famous for its use of a differential gear, previously believed to have been invented in the 16th century AD, and the miniaturization and complexity of its parts, comparable to a clock made in the 18th century. The original mechanism is displayed in the bronze collection of the National Archaeological Museum of Athens, accompanied by a replica. Depending on the historian's viewpoint, the acme, or corruption of physical Greek astronomy is seen with Ptolemy of Alexandria, who wrote the classic comprehensive presentation of geocentric astronomy. The Megale Syntaxis, Great Synthesis, better known by its Arabic title Almagest, which had a lasting effect on astronomy up to the Renaissance. In his planetary hypotheses, Ptolemy ventured into the realm of cosmology, developing a physical model of his geometric system, in a universe many times smaller than the more realistic conception of Aristarchus of Samos 4 centuries earlier. India. Historical Jantar Mantar Observatory in Jaipur, India. Further information, Jyotisha. Ancient Indian astronomy is based upon sidereal calculation. The sidereal astronomy is based upon the stars, and the sidereal period is the time that it takes the object to make one full orbit around the Sun, relative to the stars. It can be traced to the final centuries BC, with the Vedanga Jyotisha attributed to Ligada, one of the Circumvedic texts, which describes rules for tracking the motions of the Sun and the Moon, for the purposes of ritual. After astronomy was influenced by Hellenistic astronomy, adopting the zodiacal signs or hours. Identical numerical computations for lunar cycles have been found to be used in India and in early Babylonian texts. Aryabhata 476-550, in his magnum opus Aryabhataya 499, propounded a computational system based on a planetary model, in which the Earth was taken to be spinning on its axis, and the periods of the planets were given with respect to the Sun. He accurately calculated many astronomical constants, such as the periods of the planets, times of the solar and lunar eclipses, and the instantaneous motion of the Moon. Page needed. Early followers of Aryabhata's model included Varahamihira, Brahmagupta, and Bhaskara. Astronomy was advanced during the Sunga Empire, and many star catalogues were produced during this time. The Sunga period is known as the Golden Age of astronomy in India. It saw the development of calculations for the motions and places of various planets, their rising and setting conjunctions, and the calculation of eclipses. Bh. 2, 1114–1185, was the head of the Astronomical Observatory at Ujjain, continuing the mathematical tradition of Brahmagupta. He wrote the Siddhanta ceremony, which consists of two parts, Goladhyaya sphere and Grahaganita, mathematics of the planets. He also calculated the time taken for the Earth to orbit the Sun to 9 decimal places. The Buddhist University of Nalanda at the time offered formal courses in astronomical studies. Other important astronomers from India include Madhava of Sangamagrama, Nilakantha Somayagi and Jayashtadeva, who were members of the Kerala school of astronomy and mathematics from the 14th century to the 16th century. Nilakantha Somayagi, in his Aryabhatiyabhasaya, a commentary on Aryabhata's Aryabhataya, developed his own computational system for a partially heliocentric planetary model, in which Mercury, Venus, Mars, Jupiter, and Saturn orbit the Sun, which in turn orbits the Earth, similar to the Tychonic system later proposed by Tycho Brahe in the late 16th century. Nilakantha's system, however, was mathematically more efficient than the Tychonic system, due to correctly taking into account the equation of the center and latitudinal motion of Mercury and Venus. Most astronomers of the Kerala school of astronomy and mathematics, who followed him, accepted his planetary model. China. The astronomy of East Asia began in China. Solar term was completed in Warring States period. The knowledge of Chinese astronomy was introduced into East Asia. Astronomy in China has a long history. Detailed records of astronomical observations were kept from about the 6th century BC until the introduction of Western astronomy and the telescope in the 17th century. Chinese astronomers were able to precisely predict eclipses. Much of early Chinese astronomy was for the purpose of timekeeping. The Chinese used a lunisolar calendar, but, because the cycles of the Sun and the Moon are different, astronomers often prepared new calendars and made observations for that purpose. Astrological divination was also an important part of astronomy. Astronomers took careful note of guest stars which suddenly appeared among the fixed stars. They were the first to record a supernova in the astrological annals of the Huansha in 185 AD. Also, the supernova that created the Crab Nebula in 1054 is an example of a guest star observed by Chinese astronomers, although it was not recorded by their European contemporaries. Ancient astronomical records of phenomena like supernovae and comets are sometimes used in modern astronomical studies. The world's first star catalogue was made by Gandhi, a Chinese astronomer, in 4th century BC. Mesoamerica. El Curical Observatory Temple at Chichen Itza, Mexico. Maya astronomical codices include detailed tables for calculating phases of the Moon, the recurrence of eclipses, and the appearance and disappearance of Venus as morning and evening star. The Maya base their calendrics in the carefully calculated cycles of the Pleiades, the Sun, the Moon, Venus, Jupiter, Saturn, Mars, and also they had a precise description of the eclipses, as depicted in the Dresden Codex, as well as the ecliptic or zodiac. And the Milky Way was crucial in their cosmology. A number of important Maya structures are believed to have been oriented toward the extreme risings and settings of Venus. To the ancient Maya, Venus was the patron of war, and many recorded battles are believed to have been timed to the motions of this planet. Mars is also mentioned in preserved astronomical codices and early mythology. Although the Maya calendar was not tied to the Sun, John Teeple has proposed that the Maya calculated the solar year to somewhat greater accuracy than the Gregorian calendar. Both astronomy and an intricate numerological scheme for the measurement of time were vitally important components of Maya religion. Medieval Islamic world. The section may contain inappropriate or misinterpreted citations that do not verify the text. Please help improve this article by checking for inaccuracies. Help, talk, get involved. March 2011, this section may require cleanup to meet Wikipedia's quality standards. No cleanup reason has been specified. Please help improve this section if you can. March 2011. See also, Meyrege Observatory, Ulugh Observatory and Istanbul Observatory of Taqi Aldin. Arabic Astrolabe from 1208 AD. The Arabic and the Persian world under Islam had become highly cultured, and many important works of knowledge from Greek astronomy and Indian astronomy and Persian astronomy were translated into Arabic, used and stored in libraries throughout the area. An important contribution by Islamic astronomers was their emphasis on observational astronomy. This led to the emergence of the first astronomical observatories in the Muslim world by the early 9th century. Star catalogues were produced at these observatories. In the 10th century, Abd al-Rahman al-Sufi, as a Fi, carried out observations on the stars and described their positions, magnitudes, brightness, and color and drawings for each constellation in his book of fixed stars. He also gave the first descriptions and pictures of a little cloud now known as the Andromeda Galaxy. He mentions it as lying before the mouth of a big fish, an Arabic constellation. This cloud was apparently commonly known to the Isfahan astronomers, very probably before 905 AD. The first recorded mention of the large Magellanic cloud was also given by al-Sufi. In 1006, Ali ibn Ridwan observed SN 1006, the brightest supernova in recorded history, and left a detailed description of the temporary star. In the late 10th century, a huge observatory was built near Dahran, Iran, by the astronomer Abu Mahmud al-Khujandi, who observed a series of meridian transits of the Sun, which allowed him to calculate the tilt of the Earth's axis relative to the Sun. He noted that measurements by earlier Indian, then Greek, astronomers had found higher values for this angle, possible evidence that the axial tilt is not constant, but was in fact decreasing. In 11th century Persia, Omar Khayyam compiled many tables and performed a reformation of the calendar that was more accurate than the Julian, and came close to the Gregorian. Other Muslim advances in astronomy included the collection and correction of previous astronomical data, resolving significant problems in the Ptolemaic model, the development of the universal latitude-independent astrolabe by Aristotle, the invention of numerous other astronomical instruments, the beginning of astrophysics and celestial mechanics after Jafar Muhammad ibn Ms. Ibn Shkir theorized that the heavenly bodies and celestial spheres were subject to the same physical laws as Earth. The first elaborate experiments related to astronomical phenomena, the introduction of exacting empirical observations and experimental techniques, and the introduction of empirical testing by Ibn al-Shatter, who produced the first model of lunar motion which matched physical observations. Natural philosophy, particularly Aristotelian physics, was separated from astronomy by Ibn al-Haytham al-Azan in the 11th century, by Ibn al-Shatter in the 14th century, and Qushai in the 15th century, leading to the development of an independent astronomical physics. Medieval Western Europe. 9th century diagram of the positions of the 7 planets on the 18th of March 816. After the significant contributions of Greek scholars to the development of astronomy, it entered a relatively static era in Western Europe, from the Roman era through the 12th century. This lack of progress has led some astronomers to assert that nothing happened in Western European astronomy during the Middle Ages. Recent investigations, however, have revealed a more complex picture of the study and teaching of astronomy in the period from the 4th to the 16th centuries. Western Europe entered the Middle Ages with great difficulties that affected the continent's intellectual production. The advanced astronomical treatises of classical antiquity were written in Greek, and with the decline of knowledge of that language, only simplified summaries and practical texts were available for study. The most influential writers to pass on this ancient tradition in Latin were Macrobius, Pliny, Martianus Capella, and Chalcidius. In the 6th century Bishop Gregory of Tours noted that he had learned his astronomy from reading Martianus Capella, and went on to employ this rudimentary astronomy to describe a method by which monks could determine the time of prayer at night by watching the stars. In the 7th century the English monk Bede of Jarrow published an influential text on the reckoning of time, providing churchmen with the practical astronomical knowledge needed to compute the proper date of Easter using a procedure called computus. This text remained an important element of the education of clergy from the 7th century until well after the rise of the universities, in the 12th century. The range of surviving ancient Roman writings on astronomy and the teachings of Bede and his followers began to be studied in earnest during the revival of learning sponsored by the Emperor Charlemagne. By the 9th century, rudimentary techniques for calculating the position of the planets were circulating in Western Europe. Medieval scholars recognized their technical flaws, but texts describing these techniques continued to be copied, reflecting an interest in the motions of the planets and in their astrological significance. Building on this astronomical background, in the 10th century European scholars such as Gerbert of Aurillac began to travel to Spain and Sicily to seek out learning which they had heard existed in the Arabic-speaking world. There they first encountered various practical astronomical techniques concerning the calendar and timekeeping, most notably those dealing with the astrolabe. Soon scholars such as Hermann of Reichenau were writing texts in Latin on the uses and construction of the astrolabe, and others, such as Walcher of Malvern, were using the astrolabe to observe the time of eclipses in order to test the validity of computistical tables. By the 12th century, scholars were traveling to Spain and Sicily to seek out more advanced astronomical and astrological texts, which they translated into Latin from Arabic and Greek, to further enrich the astronomical knowledge of Western Europe. The arrival of these new texts coincided with the rise of the universities in medieval Europe, in which they soon found a home. Reflecting the introduction of astronomy into the universities, John of Sacrobosco wrote a series of influential introductory astronomy textbooks: The Sphere, a Computus, a text on the quadrant, and another on calculation. In the 14th century, Nicoloresme, later Bishop of Lisieux, showed that neither the scriptural texts nor the physical arguments advanced against the movement of the earth were demonstrative, and adduced the argument of simplicity for the theory that the earth moves and not the heavens. However, he concluded, everyone maintains, and I think myself, that the heavens do move, and not the earth, for God hath established the world which shall not be moved. In the 15th century, Cardinal Nicholas of Cusa suggested in some of his scientific writings that the earth revolved around the sun, and that each star is itself a distant sun. He was not, however, describing a scientifically verifiable theory of the universe. Renaissance period. Galileo Galilei, 1564–1642, crafted his own telescope and discovered that our moon had craters, that Jupiter had moons, that the sun had spots, and that Venus had phases, like our moon. The Renaissance came to astronomy with the work of Nicholas Copernicus, who proposed a heliocentric system in which the planets revolved around the sun, and not the earth. His De Revolutionibus provided a full mathematical discussion of his system, using the geometrical techniques that had been traditional in astronomy since before the time of Ptolemy. His work was later defended, expanded upon and modified by Galileo Galilei and Johannes Kepler. Galileo was considered the father of observational astronomy. He was among the first to use a telescope to observe the sky, and after constructing a 20x refractor telescope he discovered the 4 largest moons of Jupiter in 1610. This was the first observation of satellites orbiting another planet. He also found that our moon had craters, and observed, and correctly explained, sunspots. Galileo noted that Venus exhibited a full set of phases resembling lunar phases. Galileo argued that these observations supported the Copernican system and were, to some extent, incompatible with the favored model of the Earth at the center of the universe. Uniting physics and astronomy. Plate with figures illustrating articles on astronomy, from the 1728 Cyclopedia. Although the motions of celestial bodies had been qualitatively explained in physical terms since Aristotle introduced celestial movers in his Metaphysics, and a fifth element in his On the Heavens, Johannes Kepler was the first to attempt to derive mathematical predictions of celestial motions from assumed physical causes. combining his physical insights with the unprecedentedly accurate naked-eye observations made by Tycho Brahe. Kepler discovered the 3 laws of planetary motion that now carry his name. Isaac Newton developed further ties between physics and astronomy through his law of universal gravitation. Realizing that the same force that attracted objects to the surface of the Earth held the Moon in orbit around the Earth, Newton was able to explain in one theoretical framework all known gravitational phenomena. In his Philosophia Naturalis Principia Mathematica, he derived Kepler's laws from first principles. Newton's theoretical developments lay many of the foundations of modern physics, completing the solar system. Outside of England, Newton's theory took some time to become established. Descartes' theory of vortices held sway in France, and Huygens, Leibniz, and Cassini accepted only parts of Newton's system, preferring their own philosophies. It wasn't until Voltaire published a popular account in 1738 that the tide changed. In 1748, the French Academy of Sciences offered a reward for solving the perturbations of Jupiter and Saturn, which was eventually solved by Euler and Lagrange. Laplace completed the theory of the planets towards the end of the century. Edmund Halley succeeded Flamsteed as Astronomer Royal in England, and succeeded in predicting the return in 1758 of the comet that bears his name. Sir William Herschel found the first new planet, Uranus, to be observed in modern times in 1781. The gap between the planets Mars and Jupiter disclosed by the Titius-Bode law was filled by the discovery of the asteroid Ceres and Pallas in 1801, with many more following. At first, astronomical thought in America was based on Aristotelian philosophy. But interest in the new astronomy began to appear in almanacs as early as 1659. Modern astronomy. In the 19th century it was discovered that, when decomposing the light from the sun, a multitude of spectral lines were observed, regions where there was less or no light. Experiments with hot gases showed that the same lines could be observed in the spectra of gases, specific lines corresponding to unique elements. It was proved that the chemical elements found in the sun, chiefly hydrogen and helium, were also found on Earth. During the 20th century, spectroscopy, the study of these lines, advanced, especially because of the advent of quantum physics that was necessary to understand the observations. Although in previous centuries noted astronomers were exclusively male, at the turn of the 20th century women began to play a role in the great discoveries. In this period prior to modern computers, women at the United States Naval Observatory, USNO, Harvard University, and other astronomy research institutions began to be hired as human computers, who performed the tedious calculations, while scientists performed research requiring more background knowledge. A number of discoveries in this period were originally noted by the women computers, and reported to their supervisors. For example, at the Harvard Observatory, Henrietta Swan Leavitt discovered the Cepheid variable star period luminosity relation, which she further developed into the first method of measuring distance outside of our solar system. Annie Jump Cannon, also at Harvard, organized the stellar spectral types according to stellar temperature. In 1847, Maria Mitchell discovered the comet using a telescope. According to Louis D. Eigen, Cannon alone, in only 4 years discovered and catalogued more stars than all the men in history put together. See 4 more women astronomers. Most of these women received little or no recognition during their lives due to their lower professional standing in the field of astronomy. Although their discoveries and methods are taught in classrooms around the world, few students of astronomy can attribute the works to their authors, or have any idea that there were active female astronomers at the end of the 19th century. Cosmology and the expansion of the universe. Comparison of CMB, cosmic microwave background, results from satellites COBE, WMAP, and Planck documenting its progress in 1989 to 2013. Most of our current knowledge was gained during the 20th century. With the help of the use of photography, fainter objects were observed. Our Sun was found to be part of a galaxy made up of more than 1,010 stars, 10 billion stars. The existence of other galaxies, one of the matters of the Great Debate, was settled by Edwin Hubble, who identified the Andromeda Nebula as a different galaxy, and many others at large distances, and receding. Moving away from our galaxy. Physical cosmology, a discipline that has a large intersection with astronomy, made huge advances during the 20th century, with the model of the hot Big Bang heavily supported by the evidence provided by astronomy and physics, such as the redshifts of very distant galaxies and radio sources, the cosmic microwave background radiation, Hubble's law, and cosmological abundances of elements. New windows into the cosmos open. Hubble Space Telescope. In the 19th century, scientists began discovering forms of light which were invisible to the naked eye. X-rays, gamma rays, radio waves, microwaves, ultraviolet radiation, and infrared radiation. This had a major impact on astronomy, spawning the fields of infrared astronomy, radio astronomy, X-ray astronomy, and finally gamma-ray astronomy. With the advent of spectroscopy, it was proven that other stars were similar to our own Sun, but with a range of temperatures, masses, and sizes. The existence of our galaxy, the Milky Way, as a separate group of stars was only proven in the 20th century, along with the existence of external galaxies, and soon after, the expansion of the universe seen in the recession of most galaxies from us.